and motivational part. So let me remind that we are dealing with so what I discussed yesterday. I discussed Schlesinger systems, which arise in the problem of isomorphic deformations of systems of linear differential equations with meromorphic right-hand side and with simple poles. And I discussed how we can construct the tau function corresponding to such system. And the tau function, it contains most, well, it has most of the properties, encodes most of the properties of the Schlesinger system and of the corresponding Riemann-Hilbert problem. And then we discussed various variational formulas on the moduli space of Riemann surfaces, or on Hurwitz spaces or moduli spaces of holomorphic differentials. So now I am going to start putting that together. So the Riemann-Hilbert problem, which we are going to use. So first I'm going to start from some Hurwitz space. Consider a Hurwitz space with some multiplicities of R of the poles, so HGD. So HGD is a Hurwitz space. Hurwitz space. A meromorphic function f, so it's space of pairs LF, while a meromorphic function f has poles of multiplicities M1, etc. MR. So the sum is equal to degree of the function. And I assume that all zeros of the differential df are simple. So if we have, well, so an element of this space is a branch covering with some multiplicities of poles at infinity and some simple branch points. And function f gives projection of this Riemann surface to the complex plane Z. So, of course, generically, the matrix Riemann-Hilbert problem cannot be solved explicitly. The transcendentality grows as grows the number of poles and the dimension of the problem. Say, for 3 poles, 2 by 2 matrices, essentially the solution of Schlesinger system reduces to hypergeometric function. For 4 poles and 2 by 2, it's Paine-Levé 6, already the transcendental solution. The more poles you take, the higher dimension of the matrix you take, the more transcendental functions you get. In some special cases, although, when the Riemann-Hilbert problem has special type, we can solve it explicitly. And an example of such problem is given by, well, let's consider the monodromy matrices, which are the matrices of quasi-permutation. So the matrix of permutation is a matrix where in each column there is only one non-vanishing entry, and in each row there is only one non-vanishing entry, and it's equal to 1. But there is a correspondence between elements of symmetric group and such matrices. Matrix of quasi-permutation, you put some non-vanishing numbers instead of ones. Right? So you get something like that. So the group of such matrices is a normalizer of the torus, if you think about that. And it turns out that if all monodromy matrices have this form, so if the monodromy group is a subgroup of the torus normalizer, then one can solve the Riemann-Hilbert problem explicitly in terms of the holomorphic objects associated to certain branch covering. So roughly speaking, what we do is from this monodromy matrix, first we put ones against instead of all these stars, then we get matrices of permutation. To each matrix of permutation, I assign an element of the symmetric group SD, and then I can cook a branch covering. I have positions of singularities, I have a set of elements of the permutation group corresponding to, of symmetric group corresponding to that, and the product is 1, since the product of monodromy matrices in Riemann-Hilbert problem is 1, and I naturally come to object like that. So I get a compact Riemann surface. Once I got compact Riemann surface, I can do whatever I want. I have everything here. And in particular, I can construct my matrix psi in terms of so-called Siege kernel. But I'm not going to discuss that. I don't have time for that. So in terms of of Siga kernel. It's some kind of Cauchy kernel in spin bundle on a Riemann surface. What is interesting for us is the isomorphic tau function. The equations for isomorphic tau function, the general equations for an arbitrary Riemann-Hilbert problem, they look like that. It's a residue 1/2, a residue at zj of trace of a square of lambda, where a of lambda is the coefficient from the linear system. So this is the equation for the Jimbo-Miwa tau function. And here, in the context of this Riemann-Hilbert problem of that type, this equation can be written like that. It's 1/12 pi I suppose. The coefficients can be wrong, of course. Residue at zj of the following thing. Here I put the Bergman projective connection minus another projective connection, which I didn't define yet, over df. So what is this SB? SB, as you remember from yesterday, on the diagonal, the canonical bimeromorphic differential has the following standard asymptotics, minus zeta of y square plus, and the next term, the term with first order pole vanishes by two reasons. First, W is symmetric, and second, I cannot have only one residue. Right? And this second term is this Bergman projective connection, d zeta of x, d zeta of y on the diagonal. So it's exactly that object. What is this SDF? Well, SDF is just Schwarzschild derivative of f with respect to some local parameter. So the difference of two projective connections is a quadratic differential. Ratio of quadratic differential and df is one form. This one form vanishes exactly at the zeros of df. So the residues can be taken. So we get something which at least looks reasonable. Now, the question is about compatibility. One can check compatibility using this long way, going from Schlesinger system. From psi, we go to Schlesinger system, then we know that this is actually not just some Hamiltonians, but the Hamiltonians of the which have this form, and then compatibility is automatic. But of course, one can also check this directly, that the cross derivatives coincide, using the Rauch variational formulas, which we discussed yesterday. The formulas, variational formulas for the differential doublet. So we get something. Now, already from that definition, we can say something. We can say, for example, how the tau function transforms under the change of symplectic basis on my Riemann surface. So we can say, for example, how it transforms under Möbius transformation on the base. But actually, this formula can be explicitly integrated, and the result turns out to be surprisingly complicated. I just write it down for your information to show that actually the object is rather non-trivial. So you see, we were trying to play with that. In genus 1, you get something close to the Dedekind theta function. So in high genus, we expect to get some high genus analog of the Dedekind theta function. And here we have a different structure than what Andrew was discussing, and from this Zograf f function, because he has the moduli space, but he uses the Schottky uniformization. Here you have additional structure. You have the function, the meromorphic function. So, but still, the naive guess would be what should be the high genus analog of the Dedekind theta function. You say you can multiply all even non-vanishing theta constants, for example. That turns out to be not the case, and the proper formula looks like that. And here it's going to be slightly long. So these are, here I have some directional derivatives in the direction of the vector of holomorphic differentials applied to theta function on my Riemann surface, computed at the vector of Riemann constants. The objects, unfortunately, I don't have really time to define, but I'm more or less sure that everyone here is fluent in these objects. So here I have some object w to the power 2 over 3. This w is just Wronskian of holomorphic differentials. So it's a determinant. First row consists of differentials themselves, and in the second row I have the derivatives, etc. This is the object which vanishes exactly at the Weierstrass points of my Riemann surface. And by the way, this thing also is a corollary of the Riemann vanishing theorem. And I also dress with something. Here I forgot to introduce some notation. Let's define the divisor of my differential df to be sum of dj small times dj large. dj are coefficients, d large, j are points. If, say, function f, well, has simple critical points and simple zeros, then these coefficients are equal to +1 for zeros and -2 for poles, of course. So, and here I have some combination of prime forms, e of dj dl to the power dj dl over 6 divided by product of prime forms from x to dj to the power g minus 1 dj over 6. Well, there is some internal beauty in this formula, which is not quite obvious when you look at it, probably. But the idea is that to get the higher order, higher genus analog of the decaying eta function, from that point of view, we have to differentiate, well, theta function g times. So you see, usual eta function is basically theta 1 prime, right, to some power. Here we have, well, derivative for the g, and theta 1 is just theta function computed at the vector of Riemann constants in genus 1, because it's just tau plus 1 over 2 is the vector of Riemann constants. It's a Riemann constant. Here you take derivative for the g and compute it at the vector of Riemann constants. Here there is, you see, left-hand side depends only on moduli. In the right-hand side you have a point of your Riemann surface, x. Here, 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 and here. Actually, this dependence goes away. So, but we don't simplify. We cannot simplify it by choosing it somewhere. We just lose the structure. Surprisingly enough, the proof is quite difficult. I don't know why. All the machinery of variational formulas has to be used. In particular, one has to, well, get variational formulas for the vector of Riemann constants, for the prime forms. All this business has to be differentiated, and it's pretty long proof. But okay. As I said, so tau function is of course just a function. Well, locally it's a function. Globally, it's going to be a section of a line bundle over Hurwitz space, right? When I look at this formula, it seems that there is dependence on the point of Riemann surface. Left-hand side, well, left-hand side. Now let's put arguments. Locally depends on my Riemann surface on some weak marking, weakly marked Riemann surface, and function f. The right-hand side, it seems that it depends on the point of my Riemann surface, but a simple lemma shows that this dependence is trivial. So it's not there, in fact. So, okay, local formula is good, but what about the global properties of this object? The global properties can be easily deduced from either from here or from definition. Well, from definition we can get almost everything except constant factors. You see, to get the holonomies, well, basically the equations give us the connection, but to get the monodromies of this connection, we should really integrate. Right? We have to find the section, and then we can determine the monodromies if they are independent of moduli. All the monodromies which are moduli dependent, one can deduce from here. So essentially, well, first is how tau transforms under the change of symplectic basis. Of course, it transforms essentially as the automorphic form. So tau of L A alpha prime or tilde B alpha tilde F tau L A alpha B alpha. F is the determinant of CB plus D, where this matrix DCBA is the transformation between the basis A tilde and the old basis A tilde B tilde. So it looks well. So here we see the lambda class already entering, but now I didn't study yet the global behavior. I have to look what happens at the boundary. But if I want now to compactify, say, the Hurwitz space and consider, say, the space of admissible covers, then I have to factor over the Möbius transformations, right, on the base of the covering. And well, tau function, of course, it's not Möbius invariant as it's written here. But to get the Möbius invariance, we cook a different function. We take eta, which is equal to this tau function to the power 24 times n minus 1, where n is number of critical points of function f, no zeros of differential df, and divide by product of zj minus zk to the power 6. Here is Van der Monde of critical values of my function to a certain power, and these powers are adjusted such that this object is Möbius invariant. So when I apply Möbius transformation in Z plane on the base of my covering, this object remains invariant, and this depends only on the choice of canonical basis. The transformation, well, one can basically, this determinant comes in the power 24 times n minus 1. So indeed, this eta, well, is a section of the Hodge line bundle.
What is more n?
Number of branch points. Its notation is exactly like yesterday. R? Well, it's just the number of poles. Number of poles. There is a problem here that you remember the space of holomorphic differentials, which I discussed yesterday, and it's probably my mistake that I used in the context of Hurwitz spaces. I use m's to label the multiplicities of poles of function f, and in the context of the spaces of holomorphic differentials, I use them to label the multiplicities of zeros of the differential. I'm sorry for that, but here, so m1, etc., mr, these are poles, and n is number of branch points. Okay, so we got essentially here we get an explicit section of the Hodge line bundle, and then by studying if we can compactify the Hurwitz space and look at the asymptotical behavior of this object at the boundary, then we can express the lambda class in terms of the boundary classes. And this indeed can be done. So if we look at the space of admissible covers, so how the space of admissible covers looks like. We take our covering, which is somewhere there, and then all branch points we split into two groups, say z1, etc., zk, we put in one group, and zk plus 1, etc., zn, we put in another group. And then we take this bunch of points and multiply them with epsilon. Right? Then somehow in the limit, and then we put epsilon to 0. In this way, we get a component of the boundary of the space of admissible cover of codimension 1. Well, because essentially, when you do that here, forgetting about the covering, just take the punctured Riemann sphere. In the limit, if we take a bunch of points on the Riemann sphere of punctures, multiply them simultaneously with epsilon, and send epsilon to 0. In the limit, we get essentially two Riemann spheres attached by a plumbing construction. One Riemann sphere with punctures z1, etc., zk, and another zk plus 1, etc., zn. The famous Knudsen construction for the compactification of the space of punctured spheres. Right? Now, if I have something on top, yeah, of course, to get codimension 2, we take 3 groups, and say first we multiply the points from one group with epsilon. It's gone away. Then we get, well, the remaining points again. We split into 2 groups, etc. But since the space of admissible covers is an orbifold, we will be interested only in boundary of codimension 1. Essentially, an orbifold up to some small delicate points. So when we play this game with the base of the covering, something happens with the covering itself. And of course, the covering splits the Riemann surface which we have on top. It splits into 2 parts, and each part is not necessarily connected. So we get a bunch of well, some Riemann surface which is not necessarily connected here, and some Riemann surface which is not necessarily connected here. So something like that we get. And they are glued, well, over some point. So if I send epsilon to 0, then I can say that these 2 coverings are glued now at, well, at the point which projects down to 0. So here I had something on the right and something on the left. Well, one should still remember that sometimes this Riemann surface was connected initially. Anyway, could be something like that. Now, what happens at this point? You see, when I take a collection of points on the base and put them in one group, then how do I get, say, the right-hand side Riemann surface? I have to multiply the permutation elements corresponding to these points. And in the limit, say, if I take a Riemann surface, which I have here on top, but here I just write a schematic picture. Say, here we have z1, etc., x1, etc., xk, which are points of my Riemann surface. Here I have xk plus 1, etc., xn. So to each of these points we have a permutation assigned, sigma 1, etc. sigma k. Here we have sigma k plus 1, etc. sigma n. Now, if these points are put together, then they form a point, the branch point of some non-trivial multiplicity, which we can denote somehow. Well, there could be several cycles, and the lengths of these cycles we can denote, say, by m's occupied. So let's say L1, etc., Ls. So, well, then we get a boundary component. So what labels all these boundary components? We can denote them by, say, delta, then the number k should enter, and these numbers, the lengths of cycles which we get as products of these permutations. So then we get a boundary component of this type. K stands for the number of points which we glue together, and Ls, well, are lengths of the cycles of the multiple branch point which is formed. Now you see, of course, the number of these boundary components is much higher than in Deligne-Mumford compactification of moduli space, right? Wow. And in particular, some of them, of course, project down to the boundary of the Deligne-Mumford, but some not. Some can sit inside. And, well, so on the moduli space, of course, we cannot express the lambda class in terms of the boundary components. Here we can. And the formula which we get, if we take into account properly the local parameter near this boundary point, which is some separate discussion, and I think I'll skip it, the knowledge of the explicit formula for the section of the Hodge bundle gives us a formula for the lambda class, which roughly looks as follows. So just to give an idea of what's going on, so sum for k from 2 to g plus d minus 2, some coefficient, and this coefficient looks like that. Sum from 1 to product from 1 to s of this ls of the li, k times n minus k over 8 n minus 1 minus 112 times d minus sum of 1 over si li. That's all. Times this divisor delta L1, etc. L S K. So that's the formula. And in hyperelliptic case, this formula was written by Karnalba and Harris in '88 for an arbitrary space. It was not known. So maybe algebraic geometers knew how to get it, but they never wrote it down explicitly. And here it comes from pure analytical consideration. And by the way, the Karnalba-Harris formula for the hyperelliptic case can be, of course, obtained just from product of usual even theta constants. You take all non-vanishing even theta constants, multiply them, look at the boundary behavior. Of course, we again get some automorphic form, the section of the lambda class, and look at the boundary behavior, get a similar formula. Now, there is more in the tau function. Somehow, the Hurwitz structure is really essential. It's essential that we not only have a point of the moduli space, but also a function. And one can see that, for example, looking at the space of polynomials. Let's consider the Hurwitz space to be space of polynomials of degree d. So the Riemann surface is just a Riemann sphere. And denote this polynomial by p. So polynomial of degree d. Then the tau function of this polynomial is just up to a factor. It doesn't matter. It's just the resultant of p prime and p double prime. So that's the resultant vanishes if two zeros of p prime coincide. And that's so somehow it gives you the fusion of the kin theta function and the notion of resultant. Strange. And somehow the disadvantage, quote unquote, with respect to the Zograf f function is that we need an additional structure here. We need a function. The advantage is that we know the modular transformation, which is not known for the f function. So it's not known how a function transforms under the action of the mapping class group. Here, well, there is no mapping class group. There is just, well, symplectic transformation. And the transformation is quite nice. OK, so that's the case of the Hurwitz space. Here, there is no spectral theory so far, although if one does things properly, one can use this tau function to compute the determinant of the Laplacian operator corresponding to this metric which Sergio was interested in, modulo of df square. So if you look at this metric is very intuitive. You take a branch covering with the Riemann surface, you realize a branch covering of the complex plane. And this is your metric manifold. So it has asymptotically plane, asymptotical planes, right, and in additional conical points. Then if you develop, well, of course, then determinant of Laplacian is some strange object which you can define using variational formulas. You can subtract this something corresponding to the asymptotical regions. So this is not very well defined object, but you can define it rigorously, and then using this tau function you get an explicit formula for that, which looks like that. Determinant of delta divided by determinant of imaginary part of matrix of the periods, which is basically the determinant of the matrix of scalar products of holomorphic differentials, is equal to the modulus square up to a constant. Anyway, this determinant you cannot invariantly define. Well, you can only define its moduli, its dependence on moduli. The constant cannot be fixed naturally. Times tau function of Riemann surface modulus square of the tau function. So moduli the fact that this is a strange object, such a formula holds. But somehow more interesting context is when you have a flat metric on compact manifold, and this is the context of the moduli space of holomorphic differentials, which I am going to discuss now. So in the case of Hurwitz space, this formula, well, it holds, but it's somehow strange. In the case of the moduli space of holomorphic differentials, one can develop a similar formalism, and there you get the formula for the determinant of the Laplacian in flat metrics with trivial holonomy. So let me discuss that now. So let me change the context. And turn back to the moduli space of holomorphic differentials, which we denoted by Hg, M1, etc., Mg. So let me recall that Li was a basis in the relative homology group H1 of L relative to the divisor of zeros of differential W. So L is Riemann surface now, W is holomorphic one form with multiplicities of zeros and 1, etc., Mg. And the sum is, of course, 2G minus 2. And so Li was a basis here, and Li star was a dual basis in the homology group of the punctured Riemann surface. When I delete this zeros of W, so here I have, in addition to absolute homologies, I have also the integrals between zeros of W, and here I have circles, small contours around the zeros. So basically, if Li is a contour between, say, x1 and x2, if this is Li, then Li star is this one. And between A and B cycles, the duality is standard. Okay, then in this context, the definition of the tau function is exactly the same as in the case of Hurwitz space. Just the connection to the Schlesinger system is lost. So the good thing about tau function Hurwitz space is that it comes from Miwa-Jimba, from Eisenhower-Röming deformation, Miwa-Jimba tau function, and etc. Riemann-Hilbert problem. Here it's lost. But formally, the definition looks exactly the same. We take the set of homological coordinates, d by dz, I denote them by zi, right, of logarithm of tau, which now depends on a Riemann surface. Of course, it depends on, again, on basis of homologies, on weak marking, and on the differential. And here I have, let me check the coefficient, minus 1 over 12 pi I, integral over dual cycle of the following projective connection. Here I have the Bergman projective connection minus projective connection SW over W. What is SW? SW is defined in analog to the connection SDF. It's a Schwarzschild derivative of integral of W with respect to any local parameter. So again, I got some definition. Now consistency has to be checked directly using the variational formulas we have. One cannot appeal to the formalism of the Schlesinger system. So one has to develop all these variational formulas, as I discussed yesterday. Check that cross derivatives are equal. Again, one can integrate this. The result of integration, so we get exactly the same formula as before. So after integration, we get exactly the same formula as before, where just now we take the divisor of W and write it as sum of di times di. So di, well, we take the old formula and plug in, just change the notations there. And again, we get the formula for the tau function. Now, you see, in the case of genus 1, G equals 1, the previous formula which I had, it doesn't coincide with the Dedekind theta function, strictly speaking, because you have additional poles, you have some additional ingredients. Here, if G is equal to 1, then this divisor is empty. You have nothing. And then this is just a Dedekind function. So then tau is just eta of b divided by a. So the homological coordinates boil down to the b period and a period. All the integrals between zeros go away, and we have this. So in this case, we indeed can talk about this analogy to the Dedekind. And then the formula for the determinant, it becomes already rigorous. Now we can take the Laplace operator in this metric with trivial holonomy. Well, here one has to take the self-adjoint extension. The self-adjoint extension is the Friedrichs extension. For other extensions, some people know what happens. I don't know. Obviously, there is a formula relating these determinants in different extensions, but it's not my. So here we put the matrix of scalar products of holomorphic differentials. The area is, by the way, just a simple thing. It's I think imaginary part of sum of ai bi bar. Right? If I take double integral of w which w bar, then I can put it on the boundary and compute using the Riemann bilinear identities. So the result is going to be modulus square of tau function square. You see, of course, one has to observe something here, that determinant is something which is independent on Tarelli marking. The area is also independent, right? But this part, that in B, and this part, they of course transform under symplectic transformation, but they transform simultaneously, and somehow already from that formula we see that tau transforms like a section of the lambda class. But here, in this context, we cannot again, tau function is not scaling invariant. You see, here we don't have Möbius transformations anymore because, well, there is no natural Riemann sphere. But there is a natural group of linear transformations acting on my W. I can, well, essentially it's rescaling. I can take W and multiply it with some number. And the tau function is not invariant under this. And in the case of Hurwitz spaces, we cured that by dividing out some Wronskian. In this context, we don't have a Wronskian. So we have to do something. And then we can say, okay, so what do we do? This is the first difficulty. Second difficulty is that there is no natural to write some algebra geometric relations in the. By the way, that relation was written, of course, in the rational Picard group. If you want to write something like that here, then the problem is that there is no natural, or it's not known, the natural compactification of this space for arbitrary multiplicities of zeros. What is, of course, trivial is that there is, well, if all multiplicities are equal to 1, then we embed this space to the Hodge vector bundle over Deligne-Mumford, and here you are. This is the natural compactification. So, and on Hg, for the tau function on Hg1, etc. 1, all multiplicities are 1. we can, using the tau function, we can find the relation between the lambda class, between the tautological class psi, which is responsible for the rescaling of my tau function, and boundary divisors. And what is the boundary of this space? The boundary consists of course, there is Deligne-Mumford boundary, D0, and dj for j running from 1 to integer part of g over 2. And there is also the locus which doesn't project to the boundary of Deligne-Mumford when two zeros of my differential glue together. So here, this is essentially the stratum, well, the part of the stratum AG2, 1, etc. 1. And these classes will be dependent with some coefficients which do I have it? Do I have them here? I didn't write them down explicitly. Maybe I just write down this formula for completeness. Well, the formula which you get here looks as follows. Lambda is equal to g minus 1 over 4 psi, so this is just the homogeneity coefficient, plus 1 over 24 delta, or I wrote there d deg, plus 1 over 12 d0, plus 1 over 8 sum of dj from 1 to integer part of g over 2. So here the additional element is this tautological class, which okay, so that's as far as we can go in the case of these moduli spaces, and here's the spectral interpretation of that. And you see what is nice about this formula comparing to the formula of holomorphic factorization of determinant of Laplacian in Poincaré metric. Well, simultaneously nice and bad. The nice thing is that, well, here in the case of, if I put here Poincaré metric, then I get here modulus square of some holomorphic function times e to the power some Liouville action, which is the formula of Zograf-Takhtajan, which was somehow the mathematical version of the Belavin-Knizhnik theorem, right? And this e to the power Liouville action cannot be holomorphically factorized because it gives the Keller potential of the Val-Peterson, right? Here, if I'm trying to use this as a Keller potential for something, I'm going to fail because, well, second, if I take logarithm of that, take second holomorphic anti-holomorphic derivatives, I get 0.
I have a question. What do you mean by tautological class in this context?
Well, this means if I'm thinking about the sections, the section of this, well, it transforms as the determinant of BC plus D. And section of this, if I multiply W with a constant, then section of tautological class is multiplied with a constant. People told me that it's called like that. So if you so it's
Riemann band defined by zeros of differential.
Well, yeah, the zeros remain constants. Yeah, that's right. You just take the rescaling of the differential and so it's when you take, say, what to get CP1 from C, you take C2 and you factor over multiplication. So then you get CP1 and the line over each point. So that's exactly the. Okay, so yeah, what I was. Yeah, that here we don't have any Liouville action, so this thing cannot really serve as any Keller potential. So if one tries to develop, say, if one thinks of finding some Keller metric on the moduli space of holomorphic differentials, and one can, of course, look at the natural determinant of Laplacian, one would like to reproduce this formula, that dd bar of the determinant of Laplacian and Poincaré metric is a Keller potential for Weil-Peterson. If one thinks of finding an analog of something like that here, then one sees that one cannot do that because the holomorphic factorization is complete somehow. Yes. Well, to prove that, the variation of tau function, well, it's basically you take everything. Well, we have just a definition, and then we have an explicit formula. Then one has to show that the variational formulas for the determinant, they coincide with the variational formulas for the tau function, right? The first variation with respect to holomorphic and with respect to anti-holomorphic. And that can be done. You go step by step from the beginning. You don't appeal to the hyperbolic geometry at all. You just take Green's function, take the heat kernel, and step by step differentiate all of that with respect to the flat coordinates. The basic idea of the variation is always the same. When you differentiate with respect to A coordinate, you get something with the jump on B cycle. And then you can write it down in terms of other objects which have jumped there.
And you don't get any contribution from conical.
In which sense? The contributions from conical points, they are there because you also, well, if you change the position of the conical point, of course.
I mean that in case of Takasaki graph, when we consider Riemann surface with puncture.
Oh, but this is not a puncture.
Yeah, but of course not puncture.
Metric is.
Yeah, not saying, but I wonder why these conical points do not give any contribution with this case.
That's a philosophical question. I don't know. I don't. Well, maybe there is an explanation, but you see, if you take not the Friedrichs extension but some other, then I suppose you will get some terms which are not factorizable here. For example.
Absolute value of omega square.
What?
The absolute value of omega square defines a flat matrix on the surface, but it has a singularity.
Conical singularities, of course.
That can produce such a topological class or
no? Again, this is this connection. Well, maybe, but I'm not qualified to comment on that.
This formula for the divisor can be understood as if you take PD bar both sides of the equation, then you get some current. And so this is basically this equation, curvature equation.
The curvature here is essentially
lambda is produced by dt bar of logarithm of
That's right. In a sense, this is... I was just about to talk about this a little bit. So, I wanted to talk about that in the following context. Just referring to the ergodic theory. So, just some small... so, in ergodic theory, there is so-called Zorich-Kontsevich cycle. And this is the following thing. You take a Riemann surface, a flat Riemann surface, and you consider a Teichmüller flow on that. So you take a pair Riemann surface holomorphic differential, and you do the following. You consider SL2R action on that, which is basically you introduce a flat coordinate, Z, defined by this holomorphic differential, and in this flat coordinate you make a SL2R transformation. And you see some part of this transformation is trivial, namely the part which corresponds to the global rotation. So essentially we have the non-trivial part is SL2R minus rotations, so the coset of SO2, which is basically the same as the upper half plane, right? So, and this is called the Teichmüller disk, the one-dimensional complex manifold. If we introduce the coordinate T on that, on the upper half plane, then it's with respect to that coordinate which people consider this dd bar operator, dt d bar t. And of course one can express this operator in terms of the homological coordinates. So the formula for that, and it's not, so you see this coordinate on the Teichmüller disk is not holomorphic coordinate with respect to the homological one. So the complex structure here is different. So Teichmüller